Tony, thanks for the invitation to come and speak here. It's always nice to be at IAS. So this is going to be a talk about unconditional pseudo-randomness, in particular fooling a certain low-level complexity class, intersections of low-weight half-spaces. I should say this is joint work with Li-Yong Tan of TTI Chicago, and I should also give him credit for having done the overwhelming share of the work on the slides. I'm essentially using slides that he made up. So if you like the talk, he should get the credit, and if you don't like the talk, of course, I should get the blame. Okay, so it's going to be a talk about intersections of low-weight half-spaces. We can also think of these as polytopes, and I should say right out front, I'm going to be exclusively concerned with the domain which is the Boolean hypercube. You can think of it as -1, 1 to the n, 0, 1 to the n, it doesn't really matter. So here's a pretty picture of a polytope. Again, it's just the intersection of some half-spaces or linear threshold functions, whatever you want to call them. I suspect we all know this already, but just to make it explicit, each one of these constituent half-spaces is a Boolean valued function. It's a function which just takes the sign of a linear form. So we have a weight vector, a real vector of coefficients. We have a threshold value. You look at which side of the hyperplane defined by w dot x equals theta your point is on, and you either output true or false. And the polytope is a collection of all points that are on the true side of this. So intersections of half-spaces come up all over the place within theoretical computer science and other fields. We can think of such a thing as the set of feasible solutions to a 0-1 integer program. These guys also come up in different areas, combinatorics, optimization, and so on and so forth. Okay? So these are the functions we'll be thinking about. How do we sort of understand the complexity of an intersection of half-spaces? Well, let's talk about a single half-space first. Okay? If I have a single linear threshold function or half-space, sine of w dot x minus theta, again, we're only concerned with what happens over the discrete Boolean hypercube. Okay? So in general, to describe, of course, a hyperplane in Rn, I have to have a real coefficient vector. But since I only care about what happens on these 2 to the n discrete points, it's a very standard fact that I can actually take the weights, the coefficients of the linear threshold function, to be integers. I don't need them to be crazy real numbers or anything like that. And the same for the threshold. Okay? So we're going to be thinking about 2 different measures of sort of the complexity of our intersection of half-spaces. If I have a polytope like this, an intersection of half-spaces, one obvious complexity measure is, well, how many half-spaces do I have? How many faces are there of this polytope? That's k. But we'll also be concerned with this other notion of sort of the complexity or simplicity of each individual linear threshold function, each individual half-space. And the way that we'll quantify that in this talk is by just thinking about its weight. So for us, each of the linear threshold functions will be defined by an integer weight vector, like I said before. And the weight of a half-space is just going to be the largest magnitude of any one of those coefficients. Okay? So we look at the largest individual coefficient. It's an integer. And that's going to be what we call the weight of our half-space. So just to remind us of a little bit of folklore in this area, it's well known that every n-variable half-space can be represented over the Boolean cube with these integer coefficients. And in fact, the integers don't have to be too obscenely large. N to the n or n factorial turns out to be big enough. It's actually an interesting fact due to Hastad from 20-something years ago that there are some wacky half-spaces which actually require integer weights to be this large, to be n to the order of n. Okay? We'll be dealing, unfortunately, with much, much smaller integer weights in this result. Let's see, what else do I want to say about this? Not too much. So yeah, like I said before, we'll be thinking about our polytopes. When we think about an intersection of k half-spaces, the 2 key parameters we'll care about are the number of faces, this number of half-spaces we're intersecting, and the largest weight of any half-space. And I'll use this parameter t to define this, to denote this maximum weight throughout the entire talk. Okay? So I should mention, again, because this talk is going to be dealing with situations where t is quite small, in general, like I said, the weight of a half-space could be as large as n to the n. It could be really enormous. But even intersections of half-spaces of weight 1 already capture some pretty non-trivial and interesting functions. So for instance, any CNF formula, okay, any and of ors, where if we have, if it's a size k CNF formula with k clauses, can be expressed as an intersection of weight 1 half-spaces. And these guys can represent considerably more than that as well. You can capture intersections of majorities, a bunch of different functions. Even if you have very small weights, even if the largest weight is 1. For instance, you could think about you have maybe a set of forbidden points in the Boolean hypercube, and you want to have a Boolean function which outputs 1 on an input point from the hypercube, if and only if it's at least some minimum Hamming distance from each of these forbidden points. That's a function you can capture as an intersection of weight 1 half-spaces. Okay. So we're going to be thinking about intersections of low-weight half-spaces. In particular, we'll be looking at these from a point of view of pseudo-randomness. Okay, we'll be concerned with coming up with unconditional pseudo-random generators against these intersections of low-weight half-spaces. So I suspect everybody here knows what a pseudo-random generator is already, but just to kind of have a picture of it to remind you what's going on, a pseudo-random generator for us is an explicit deterministic function. So I think of it as some little circuit, which is structured like this. It has a small number of input bits. We think of these as true, purely random bits. They're like gold coins, m input bits. And it stretches these m input bits to output n, some much larger number of pseudo-random output bits. So on input truly random, on being fed truly random input bits, it's not going to give us obviously truly random outputs, but a pseudo-random output, the output of a pseudo-random generator should have enough randomness to kind of look random to the functions that we're trying to fool. So that's exactly what the formal definition of pseudo-random generators says, right? If we have an epsilon pseudo-random generator for a class of functions, for us it's going to be certain intersections of half-spaces. What this means is it's just an explicit function, that's this g, that's the circuit we saw in the previous slide, which has the property that intersections of half-spaces, the functions we're trying to fool, are indeed fooled by these pseudo-random outputs. They can't tell the difference between given a truly random input string, so that's like really a random set of a random n vector. The probability of such a function, an intersection of half spaces, outputs 1 on one of these guys is epsilon close to the probability that it outputs 1 under the pseudo-random distribution, the distribution that's output when you feed in truly random bits to the pseudo-random generator. Okay, so this is our notion of fooling. Yeah. Yeah, of course. What this slide probably really should say, I'm going to blame Lee Young now, is that an epsilon PRG for a class C of functions is such that for every function in the class you have this property. And for us, our class will be intersections of half spaces with k faces and weight t, and we'll have a seed length, which I'll tell you about, which is a function of those parameters. Yeah, you're ahead of me. Okay, good, right. But in general, if you just say, oh, intersections of half spaces, every function can be expressed as some intersection of half spaces. Yeah. Okay, so this is maybe a silly slide or a silly picture, but it helps me at least think about pseudo-random generators. The way they're typically used is you enumerate over all the seeds, right? So it's natural to think of just the space of outputs that the pseudo-random generator, can output, its range. The range is just going to be a subset, a sparse subset of only 2 to the m points in this 2 to the n point space, the Boolean hypercube. And a PRG essentially outputs a set of points. Think of them as like these red dots, which are really nicely spread out. So nicely spread out that no intersection of half spaces can kind of distinguish their distribution from the uniform distribution. So in other words, any polytope, any function in our class, it accepts some certain fraction of the entire 2 to the n points of the Boolean hypercube. The condition of a PRG is that the fraction of the red points, right, the fraction of points in the output space of the PRG that the function accepts should be very close to this true fraction. It's within an additive epsilon of this quantity. Okay, so maybe a potentially helpful picture for intuition. And I should say, of course, if you just use a random set of points, very standard probabilistic arguments tell us that a randomly chosen set of points, a very small size, works absolutely great. But of course, you're cheating here, right? You can't have a pseudo-random generator, which is constructed using a random set of points. The point is to have an explicit construction. And that's what we'll strive for.
Does it make sense to allow the points not to be in -1 to the n, so it would be just in the continuous queue?
I guess it depends on the functions that you're dealing with. So here for our intersection of half spaces, sure, you could imagine that it can reasonably accept points which are real valued vectors instead of bit vectors. For other functions, if you're thinking about, I don't know, DNFs or some combinatorial class, it might not really be clear what it means to feed it something. Sure, you could think. You could think about it, yeah. I don't know of any work which, I tried once to do something which went along that route and it failed. But that was my own fault for not getting it to work. It wasn't that it was a bad idea.
Because if you just want to hit them, not to approximate,
right.
Then this was
that's
the weak epsilon native.
Yes, exactly. Different. Yeah, hitting set generator is a weaker pseudo-random primitive. Yeah. Yeah, you could think about that, but it makes sense, I think. Yeah. Okay. Yeah. Good. So let me tell you our main result. Our main result is that we give an explicit pseudo-random generator if you want to fool intersections of k weight t half spaces to accuracy epsilon. The seed length we achieve is polynomial in log n, polynomial in log k. K again is the number of faces of the half space, polynomial in t, and polynomial in 1 over epsilon. So this is actually going to be something, in discussing the relation with previous work, it's going to be kind of important to compare, like, places where we have a certain dependency versus other work. This will be a little important, so I'm just going to write down the result. The seed length is poly log n log k t in 1 over epsilon. And writing this down also gives you a chance to be grateful that I'm not giving a Blackboard talk because my handwriting is so bad. This is the number of faces, and t is the weight. Okay? Yeah, sure.
Weight is not the length of the
No, weight is,
So this only gets polynomial.
yeah, so this weight means that each wi is an integer, which is at most t, in each half space. I guess if I have the jth half space, its ith weight, all the coefficients, whichever, absolute value, yeah. All the coefficients, whichever arise in any half space, have to be at most t. Yeah.
What would this need to be in order to give like pure pseudorandom generators? Like,
Yeah.
we'd need, like log t, and we'd also need a bound on the.
No, I'm afraid you need log t. Sorry.
Why log
Because
log?
t could be as large as n to the n.
So it's not quite like that.
So if you had log t, that would still be like linear in n, right, for certain half spaces, which is trivial. Right, anytime if your seed length is n, that's completely trivial. Yeah. Yeah.
In some sense, in fact, here you
In fact, you
care
base-
about polynomials, right? Like you care about log n versus log square n here in some sense, right?
I mean, in the ideal result, so something that we worked for and haven't gotten yet, but we're taking another crack at it, you would just have no dependence on t at all.
Okay.
Right? If you believe that p equals bpp, then the right dependence is, I don't know, log n plus log 1 over epsilon, something like. There's no dependence on k. There's no dependence on, I guess there's still a dependence on k, but the true result presumably is significantly better than we're able to achieve. But sorry, man, this is what we got. So I'll tell you, quite a bit of the talk actually will be spent on kind of comparing with previous work and seeing the obstacles that arose and why it's not so easy even to get something like this. Okay, so just to highlight a little bit the fact that there is a contribution here in terms of what we can do. Let's consider kind of a special case of this result. Suppose that you're trying to fool just say k equals n, a linear number of half spaces. Suppose that the weight of each half space is 1, so all the coefficients are +1, -1, or 0, okay? And you just want to do it to some constant accuracy 1/10, something like this, okay? In this regime, nothing was previously known about how to do this non-trivially. No seed length, 0.99 times n was previously known. We're able to do quite a bit better. We have a polylogarithmic seed length, and I guess you can kind of make essentially all of the parameters a little bit worse and still achieve this, right? We can fool an intersection of quasi-polynomially many half spaces. They can have weight polylog n. You can fool them to accuracy, 1 over polylog n, and you'll still have polylogarithmic seed length. So it certainly is not the last word on the subject. I hope there will be substantial improvements, but it does get us something that we weren't able to achieve before.
So this is like intersections of majorities.
Yeah, you can think of that. Intersections of majorities, and we can go a little bit beyond that to like low integer weights. Yeah.
And before that, the
Yeah.
result that, I guess it was yours probably.
No, it
It's
wasn't.
Polylog intersection.
I'll give pretty extensive discussion of the previous work in a couple slides. Yeah, we'll see. So this is just phrasing things slightly differently. If you want to think about this as like, oh, I want to think of it as an algorithm instead of like a pseudo-randomness result, you can think of this as like a deterministic algorithm, say for counting the number of solutions, the number of feasible points to a 0-1 integer program. So as an optimization problem, you've got some linear form. You're trying to maximize it over the hypercube, subject to some linear constraints. But maybe we don't care about the optimization thing. We just want to deterministically have a rough estimate of how many feasible solutions there are. How many points are there in this polytope of the integer cube? Okay, so if you have k constraints, the matrix is k by n, and all the matrix entries are at most t, then just by using our PRG in the obvious way, enumerating over all the seeds, we have an algorithm which runs in time exponential on the seed length. You enumerate over all the seeds, okay? And we get an accurate estimate deterministically of this fraction of solutions. So really the only point of this slide is to highlight the fact that even for an easier problem, where you don't have to be oblivious the way a PRG is oblivious, if you're allowed to look at all these coefficients and all these half spaces explicitly, nothing was previously known about how to solve this kind of problem. Okay, and we're able to get some kind of quasi-polynomial time algorithm. Okay. So yeah, I'm going to start the comparison with previous results. This will actually take, I would say, about half the remaining talk. It's kind of giving a detailed comparison with what was known previously here. So again, what we do is handle an intersection of k, many low-weight half spaces, and we're doing it with the seed length polylog n, log k, t, and 1 over epsilon. Okay, and there are really two, I would say, most relevant previous pieces of work along these lines. They're contemporaneous, both about 7 years ago. So the first one I'll mention is this work of Gopalan, O'Donnell, Wu, and Zuckerman. These guys managed to fool an arbitrary function of k half spaces. So not just an intersection, any crazy k variable function you want, right, which depends on the output of k linear threshold functions. They could fool guys like this with a seed length, which I think was just linear in log n, in fact, linear in k, and logarithmic in 1 over epsilon. So it's a nice result, right? I mean, they're logarithmic in 1 over epsilon, which is great compared with what we're doing. They're linear in k, however, so they can't go beyond, certainly n half spaces. This is inevitable. I mean, they're managing arbitrary functions of k half spaces. It's easy to argue that you need a linear dependence in k if you want to be handling arbitrary functions on k, even input variables, okay? However, in probably the most interesting case, which is these k-face polytopes, where instead of an arbitrary function, you have an and, their methods, as I'll discuss, inherently require a linear dependence in k. Okay, so this is, one of the points of our work is to try to really get this down to logarithmic or polylogarithmic so that we can handle, polytopes with more faces, okay? So there was earlier work. This is really the most relevant work. We build heavily on this, as I'll explain. This is earlier work on fooling sort of a special class of intersections of half spaces. So Harsha, Clivens, and Mecca managed to fool intersections of k half spaces which have to satisfy a certain technical condition called tau regularity. I'll explain precisely what this is in a slide or two. For now, just think of it as sort of a technical condition, meaning that the half spaces are nice. Okay, well, I'll be much more precise soon. So they required all of the half spaces in their intersection to be nice in this sense. The smaller tau is, the smaller the regularity parameter, the nicer, kind of better the half space is, easier to fool. Okay, so for sufficiently regular half spaces, they were running in time polylogarithmic in n, I think again linear in n if I remember correctly, polylog k, and poly 1 over epsilon. Okay, so you can see what are we doing? We're sort of achieving a result like theirs, but now we have this dependence on the weight of the half space. So how does our result compare with their result? Well, as stated thus far, it's just incomparable. You have regular half spaces which have high weight. There are definitely points that live over here. Okay, and you also have low weight half spaces which are highly non-regular. If you want to see one, the half space just f of x equals x1. Obviously, this is a very low weight half space. The weight is just 1. But you can show the regularity is as bad as possible. The regularity is 1. Smaller regularity is good. Regularity is between 0 and 1. Okay, so these, as stated, the results are incomparable. However, as we'll see, we're actually doing something more general than just this result, and our general result includes what they do. It kind of subsumes both of these things that I've said so far. And this shouldn't be a surprise because we directly build off of what they do. If we didn't capture what they did, we would have done something badly wrong. Okay, so this is a sketch of comparison with previous work. For the rest of the talk, what I hope to do is sort of back a considerable ways up and get a running start on telling you about our work. I'm going to start by giving an explanation of the connection between pseudorandom generators for linear threshold for half spaces, or at least the particular approach we take to pseudorandom generators for half spaces. It turns out that it's intimately connected to central limit theorems. So this sort of analogy with, or inspiration from proofs of central limit theorems turns out to be a really nice way of getting PRGs. This was pioneered by work of Mecca and Zuckerman, and Harsha, Clivens, Mecca built on it. We build further on it. So that'll be the next chunk of the talk. And then after I've sort of gone through the necessary background, I'll tell you about our work. And we'll see how some new sort of ingredients come up in these arguments that give us PRGs from central limit theorem type proofs. Okay? Yeah.
Do you get something for intersection of low degree polynomials?
Good question. The answer is no. And there are, is it only one reason or are there two reasons? There's at least one good reason why we don't get that, which is because, let's talk about that a little later, but the short answer is no. We don't know how to extend it at this point even to degree 2 with a log k type dependence. Yeah. Okay, so this next part of the talk is going to be, again, giving us background and context so I can explain the new stuff, and it's going to mostly be about these pseudorandom generators and how they can be derived via proofs of central limit theorems, okay? Great, so what's a central limit theorem? I suspect we all remember essentially what a central limit theorem is. For a sort of fuzzy first slide on this, we can think of such a theorem as saying essentially that if you add up a bunch of independent, nice random variables, okay, it's going to converge to a Gaussian, where the mean and variance of the Gaussian that it converges to will, of course, match the mean and variance of the sum of independent random variables. Okay? So what do we mean by converges here? There are many ways that this statement could be interpreted. The relevant way for this talk, and it's very natural, as we'll see in a second, for half spaces and intersections of half spaces, is we'll always be thinking about closeness between distributions in terms of the CDF distance, or the Kolmogorov distance. Okay, what does this mean? It just means that you look at the cumulative distribution function of the first random variable, the second random variable, the two different distributions, and you ask yourself, what's the biggest difference that the CDF between these two distributions can ever have at any point on the real line? Okay, so in other words, for all theta, we're looking at the probability that the first random variable is at most theta versus the probability the second random variable, the second one for us is the normal distribution, is at most theta. And we want that to be everywhere small. So the mental picture is that if you plot the two CDFs, it should look something like this. I guess the CDF distance corresponds kind of precisely to like the maximum height of any one of these triangles we sort of see in the picture. Okay, and this it should be clear that this is a very sort of this is the appropriate measure of distance between random variables for linear threshold functions, because what is a linear threshold function? You're exactly looking at a linear form and comparing it against some threshold, right? So the probability that your linear form is less than the threshold corresponds exactly to the probability that the linear threshold function is 1, right? So this is the right sort of distance notion for LTFs. Okay, so let's get a little bit more detailed now. We're going to use in particular proofs of the particular proof of the Berry-SAN central limit theorem. This is a version of the central limit theorem with explicit error bounds. And this is the point in the talk when I want to introduce this notion of regularity. Okay, so what I'm going to mean by saying that a linear form over n variables is epsilon regular is very simple. It's just that if we scale the linear form so that the sum of the squares of all the coefficients is 1, then each individual coefficient should have magnitude at most epsilon. Okay, so maybe let me write that down. Again, since it's going to recur kind of often. So we have n coefficients. For now, of course, it's probably helpful to think of them as real values as opposed to integers. It doesn't really matter. We've scaled. This is what it means for W to be epsilon regular. Okay? So in other words, no coefficient is too dominant, sort of relative to the overall scale of all the coefficients. So what does the Berry-SAN central limit theorem say? It says that if you have a uniform random x, and you think of the random variable w dot x, where w is an epsilon regular linear form like this, in other words, no weight is too sort of big or out of whack, then in fact the CDF of that linear form will everywhere be epsilon close to the CDF of the normal distribution, with corresponding mean and variance, mean 0, variance 1. Okay, so I suspect most of us have seen this kind of statement before. And not to sort of belabor an obvious point, but it's absolutely crucial in this theorem that we actually have an epsilon regular linear form. Okay, if you have a linear form which is non-regular, then this linear form might be something like just x1, right? This one weight is obviously very large. It's not regular compared with the overall vector of weights. And you can see this is a plot of the CDF of x1. It's 0 for a while, then it's 1/2 for a while, then it's 1 for a while, I guess forever. And obviously the CDF is not pointwise close to the CDF of a Gaussian. Okay? So we really need regularity for these kinds of statements. Okay, so the way these PRGs work is they sort of build off of proofs of the Berry-SAN theorem. In particular, there's one style of proof that we're going to be centrally concerned with. You can prove the Berry-SAN theorem in a range of ways, with Stein's method, with characteristic functions, but the Lindeberg replacement method, which really corresponds to what we in theoretical computer science call the hybrid method, is really a nice approach which lends itself to very adaptable proofs, which we can use for pseudorandomness and other things. Okay? So if you haven't seen this before, it really, again, is just like the hybrid method, what we would refer to, and it's really motivated by a very simple observation about sums of independent random variables and Gaussians. What do we want to show? We want to show somehow that this sum of these nice random variables, x1 through xn, this guy is like, this bold capital Xi is like w1 times x1, where x1 is, plus 1 or minus 1, right? So the ith random variable is like plus wi or minus wi in this setting. We'd like to show that this is close to a Gaussian distribution. The Gaussian, of course, with the same mean and variance as the sum. Okay? Well, the sort of observation which leads you to the proof is that this Gaussian distribution, the single Gaussian that it's close to, can of course also just be expressed as a sum of n independent Gaussians, right? A sum of n independent Gaussians with means and variances corresponding exactly to the constituent random variables that we're adding up in the sum. This is just because the sum of Gaussians, independent Gaussians, is Gaussian, right? So we can think of the theorem, the statement we're trying to prove is that this sum of these, say, discrete random variables, these plus or minus wi's, converges to a corresponding sum of Gaussian random variables. Okay, and if you think about it that way, it's very natural to think of trying to prove the theorem by some kind of replacement approach. Maybe we can iteratively replace each of the xi's by a corresponding Gaussian, by a gi. We do this n times, right? And then just the triangle inequality applied n times. We started with this guy, the sum of all the x's. We swap out the x's for g's one by one. We'll end up with the sum of Gaussians, which is the thing that we're trying to say we're close to. So if each individual step causes us to only incur small distance or small error, then we'll get the theorem out if we can pull this off. Okay? So this is exactly this replacement method. And you can see it's just what we sometimes call the hybrid method. Great. So I'm not going to actually do the proof, but I just want to highlight some of the ingredients, some of the kind of key aspects that go into this, because we have to sort of work around some challenges related to these things and what we do. So the first aspect I want to highlight is regularity. Like we said, the theorem is simply not true if your random variables, if your w dot x on the left is not a regular linear form. So it should be natural that then, since the theorem requires that condition, the condition is going to come up in the proof. And it's not hard to sort of see how this kind of condition would presumably arise in an argument, a formal argument establishing this, right? If one of the xi's was really large, like corresponding to a non-regular linear form, or you had a very large weight wi, then presumably that coordinate would maybe be quite dominant in terms of its effect on the sum. And when you swap out that one coordinate, you probably are going to incur a lot of error. And this is in fact the case. Okay? Another ingredient which we require is that we have perfectly matching moments, or all the proofs I've seen use the fact that these moments match up really exactly. You have the mean of the Gaussian corresponds exactly to the mean of the ith random variable. The variance matches up. It's natural that you want this in the proof, right? That is the Gaussian you eventually converge to. And finally, independence, of course, is very important as well. The theorem is not true if you're adding up non-independent random variables, at least not true in general. And you can imagine independence arises in arguing this formally. Okay? So I'm not going to give you details on how the argument goes, but I just want to throw a couple of keywords up on the screen. The way you formally argue something like this is you first work with some kind of test function, right? The sort of sine function is discontinuous. It's not so nice. So the way the proof really goes is you first argue instead about some nice differentiable test function, which has nice properties. Its derivatives are not too large, this kind of thing. And here's a picture of the kind of thing you should have in mind. Some continuous differentiable function, which sort of approximates the sine function. You use essentially Taylor's theorem as the main workhorse, right? The intuition is we're trying to approximate maybe phi of some x plus delta. If delta is small, then hopefully we can say that phi of x is close to phi of x plus delta. So there's kind of a Taylor's theorem aspect to it. And at the last stage, when we want to actually pass from the nice continuous differentiable test function to the sine function, we're going to need some kind of anti-concentration, right? If our random variables put a ton of mass, like where the test function doesn't do a very good job of approximating sine, you'd be in trouble. So you have to worry about this kind of issue as well. Okay?
Where does the sine function come from?
Oh, the sine function, remember, a linear threshold function is
So then
sine
you
of
don't only care about the sign of this variable.
w dot x minus theta.
You're saying like the Berry-Essen theorem, like you're saying like.
The Berry-Essen theorem is about the CDF, which corresponds to like looking at the sine of the expectation of the sine of
I see.
this thing. Yeah, yeah, that's a good question. Yeah. Okay. Okay, so we have some sense of how the Berry-Essen theorem can be proved via this replacement method. What does this have to do with pseudo-randomness or pseudo-random generators? Well, if you write down the statement of the Berry-Essen theorem, and you look at what it would mean to have a pseudo-random generator fooling a half space, you can see that there's a pretty strong alignment here. Right? The Berry-Essen theorem says that if you look at this difference in probabilities, the probability that Gaussian is at most some threshold theta versus the truly random linear form w dot x is at most some threshold theta, Berry-Essen says that this difference is always very small. Okay? On the other hand, a pseudo-random generator is just some way of coming up with sort of randomness efficient distribution over bit strings, okay? Such that if I look at the probability again that a truly random n-bit string makes the linear form less than theta versus the probability that a pseudo-random n-bit string makes the threshold less than theta, this should be small. Okay, so there's really a pretty close correspondence between these statements, The only difference is that here I have the Gaussian distribution, and here I have some cooked up pseudo-random distribution over n-bit strings, or over n vectors, okay? So this inspires us to think, it inspired Mecca and Zuckerman at least to think, if you can come up with some pseudo-random sort of version of the Berry-SAN theorem, if you can kind of fool the proof of the Berry-SAN theorem using a small amount of randomness, right, then you'll actually get a pseudo-random generator for these functions. And that's exactly what Mecca and Zuckerman did. So they wrote this beautiful paper in 2010, which launched a line of work on coming up with pseudo-random generators for linear threshold functions, intersections of LTFs, polynomial threshold functions, so on and so forth. I'll give a cartoon version of the simplest result in the paper, which is as follows. Right, we saw how the Berry-SAN central limit theorem establishes CDF closeness, Kolmogorov distance closeness, between a Gaussian and a truly uniform, W dot x, this linear form. Okay, what Mecca and Zuckerman did is they said, hey, we're going to cook up a way of coming up with a pseudo-random distribution over n-bit strings, a randomness efficient distribution, and we'll argue, using basically the Berry-SAN theorem, that the distribution of the linear form under that sort of input is also CDF close to a standard Gaussian. Okay, so by doing this, question?
Well, why is M an M-bit?
Yes, y is generated using m bits of randomness, and the pseudorandom generator is a deterministic algorithm which stretches it to what we think of as a pseudorandom n-bit string. So this y is like the output of the pseudorandom generator when it's fed m bits of truly random input. Yeah. Good. So Mecca Zuckerman come up with a pseudorandom sort of version of the Berry-SAN theorem. And then once they have this, you compose the two arrows, and you get that the pseudorandom distribution of the linear form is CDF close, just by the triangle inequality, to the truly uniform distribution. And this is exactly what it means to have a pseudorandom generator. Okay? Good. So I'll give you a slide kind of giving a sketchy version of how their pseudorandom generator actually works. It's a really nice sort of construction. So the first thing they do is they pseudo-randomly hash all n variables, x1 through xn, into a fairly small number of buckets, like 1 over epsilon squared many buckets. So they just, in a randomness efficient way, this stage actually uses only log n random bits. They're able to throw the variables into 1 over epsilon squared many different buckets. So each bucket contains quite a few variables. Okay? The intuition is that if you have a regular linear form and you do this pseudo-random hashing, you'll end up with roughly, you won't end up with any bucket having a really disproportional amount of coefficient weight in it. Think of it as like each variable is associated with some amount of coefficient weight, the like wi squared for that xi. And if you pseudo-randomly hash like this, no bucket will have a really disproportionate amount of weight. The buckets themselves will be like an epsilon regular vector, now of length 1 over epsilon squared.
So I'm confused about
Yeah,
this.
yeah.
What is the weights come into this?
So this is, so the weights, we'll see in a second why the weights come into this.
Is this process done?
Obliviously, no, it doesn't look at the weights. It doesn't know anything about the weights, yeah. So let me get to the end of the slide, and I think it'll clear up, yeah. The next thing that they do is they independently make an assignment to the variables in this bucket, the variables in this bucket, variables in this bucket. For each bucket, they make an assignment to those variables using a 4-wise, it turns out 4 is enough, 4-wise independent distribution. So for each bucket, if you have a 4-wise independent distribution, assigning the variables in that bucket, that takes you log n bits of randomness. There are 1 over epsilon squared buckets. So the total amount of randomness they need for the second stage, which is the dominant cost, is log n over epsilon squared many bits of seed length. This is the amount of randomness it takes to come up with a pseudo-random n-bit string. Okay? And they're able to argue that this distribution over n-bit strings is going to be CDF, in Kolmogorov distance, epsilon close to the Gaussian. Okay, the way they argue this is really via the proof of the Berry-SAN theorem, or rather, I guess they can get away with just applying the Berry-SAN theorem as a black box. The intuition is that, like I said before, this is getting back to Tony's question, the pseudo-random hashing, remember, we're starting with a regular vector of weights. We don't know what the unknown half space is, but it's weight vector. For now, we're just doing a PRG for epsilon regular half spaces. So I don't know what that weight vector of the half space is, but I know it's epsilon regular. When you do the hashing into 1 over epsilon squared buckets, pseudo-random hash, I think just a pairwise independent hash, turns out to be enough to guarantee that the amount of weight that ends up in this bucket is on the order of epsilon. The amount of weight that ends up in this bucket is on the order of epsilon, so on and so forth. The sort of, if I think of each bucket now as like a mega variable, this is just for a rough intuition, whose amount of weight corresponds to the total amount of weights of all the WIs in that bucket, this 1 over epsilon squared length vector of sort of megaweights will still be regular. And now, by doing an independent assignment across each of the buckets, you can use Barry SAN on this 1 over epsilon squared length vector. So this is a high-level intuition of why this kind of construction should suffice to actually fool epsilon regular half spaces. So far, so good?
It's sort of like a combination of like, first of all, not meaning actual independence, just meaning like constant-wise independence, and then also.
So
like,
you actually do need full independence across these 1 over epsilon squared buckets to apply Barry SAN to the vector, to the 1 over epsilon squared length vector whose weights or coefficients correspond to the amount of weight in this bucket, the amount of weight in this bucket, so on and so forth. So that's why you have this 1 over epsilon squared in the seed length, because you're doing this independently for each bucket.
Yeah.
But it turns out 4-wise independence is enough here, because you just really need some moment properties. I think the 4th moment is enough for like the Barry SAN theorem. I give you kind of a simplified version of the Barry SAN theorem. There's other versions of it where like, sort of statements about the 4th moment suffice, and you can get those if you have 4-wise independence within each bucket.
Is it
Yeah.
fair to say that in the usual Bayesian theorem,
Yeah.
you get error which is like 1 over square root the number of variables? Here you're sort of
If
blowing
they
it
were
up-
all like the exact same weight.
Yeah.
Yeah.
Now you're like blowing up it to epsilon and noticing that you can essentially just think of 1 over epsilon square different variables to get that kind of error.
That's a good intuition, exactly. Yeah, we started with an assumption which only told us that we sort of had these guys being the same weight up to this like epsilon coarseness, so then you capitalize it by grouping variables together. That's a good way to think about it. Yeah, good. Okay, so this is a sketch of how these guys came up with a PRG for epsilon regular half spaces. This is just the tip of the iceberg of their paper. They do all kinds of cool things. They get the epsilon dependence down to logarithmic. There's a lot of nice stuff. In particular, one thing they do, which I will tell you a little bit about because it highlights some of the challenge in what we had to do, is they were able to extend this not just to fooling epsilon regular half spaces where all the weights are, kind of very small, but they're able to fool general half spaces. How would you do this kind of thing? How would you get around this regularity condition? So again, a regular half space looks like this. No weight is too large. Okay, a general half space might have some very large weights compared with sort of the overall scale of things. Okay? The basic approach they take to handling general half spaces is by reducing to the case of regular half spaces using a half space regularity lemma. Without going into a lot of detail about what this kind of statement says, it essentially says the following. If you have any half space, even a guy with big weights like this, which is non-regular, well, if it is non-regular, you can restrict a small number of variables, and after restricting a small number of variables, the half space will either become regular or it'll become close to constant. Almost every way of fixing that small number of variables will make the half space become very close to a constant function. So these are both good outcomes because we're happy when it's regular, and if it's close to constant, that shouldn't be very difficult either. Okay? And just a picture of sort of how this kind of thing works. It works exactly the way you would think. Well, you wish this was regular, so you fix the first variable, right? Now this weight has gone away, and you've just changed the threshold. Still not regular, we have some big weights, so you fix the second variable, the second big variable. Still not regular, you fix this guy, whoops, fix this guy, and now the remaining weights, these green guys, it is like a regular linear form. Okay, so the content of the regularity lemma says if you fix enough guys, basically 1 over epsilon squared many guys, and it still hasn't become regular, then the half space will be close to constant under almost every restriction like that. Okay. So given this kind of regularity lemma, a cartoon version of how they handle general half spaces is by just reducing to this regular case. Like I said, fixing about 1 over epsilon squared many variables is always enough by this regularity lemma. So you can think of a generic half space as that it has at most something like 1 over epsilon squared many head variables, and then it has an epsilon regular tail. Okay, here we've sorted the weights by magnitude. So how would you fool a general half space? Remember, if you're in the epsilon regular tail case, this is just for an intuitive sketch, you can fool it with the construction we sketched earlier with seed length something like log n over epsilon squared. And you might have these 1 over epsilon squared many annoying head variables to worry about, but intuitively, if I use something like 1 over epsilon squared wise independence, I can condition on whatever happens to those head variables, and then I'm in the regular tail case. Okay, so this is just kind of a very high-level intuitive view of how you might get the same kind of seed length and how they do get the same kind of seed length log n over epsilon squared for general half spaces. They use a regularity lemma to reduce to the case of regular half spaces. Okay? And again, they do all kinds of cool stuff besides this. They use branching program-based techniques to get the epsilon dependence down to log squared 1 over epsilon. fool polynomial threshold functions and so on. I'm really selling the paper short in what I'm telling you about it, but just for intuition, this is relevant to what we do. Okay, so what's going on here? We've seen that Mecca and Zuckerman introduced this sort of three-step program for fooling half-spaces, right? They fool general half-spaces. First, they recalled the ideas in the central limit theorem proof, which is for regular half-spaces. They de-randomized the central limit theorem using this nice bucket construction to get a PRG for regular half-spaces. And then using regularity lemmas, they were able to reduce the case of completely general half-spaces, fooling a general half-space, to fooling regular half-spaces. Okay? So it's a nice program. It worked well for them. Then you want to fool intersections of half-spaces. Okay, the next step. So how would you try to fool an intersection of half-spaces, an intersection of k half-spaces? A natural approach, and this is the approach that was taken in these previous works of Gopalan et al. And Harsha-Cliven's Mecca, is to just try the same three-step program. Maybe there are central limit theorems for k tuples of half-spaces or intersections of k half-spaces. Maybe we can de-randomize those central limit theorems. And maybe there are regularity lemmas which can sort of handle k half-spaces instead of a single half-space, right? If this all worked, that would be great. These two sets of papers pursued this general approach, but they kind of forked off at one point. If you remember, Gopalan et al. Got a seed length which was linear in k, okay? But they handled general half-spaces. Harsha-Cliven's and Mecca got a seed length logarithmic in k, but they needed the regularity assumption. So I'll trace a step or two through this program, and we'll see what happened in each of these two cases, because that'll lead us into what happens for us. Okay, so we're following this program. Again, to sort of recall the program, we need a central limit theorem, we need to de-randomize the central limit theorem, and we need regularity, all now for like k tuples of half-spaces. Okay? So again, like in the original case, we have a single half-space, a regular half-space. The central limit theorem tells us that it behaves like a Gaussian. We now need a corresponding central limit theorem really for a k tuple of half-spaces, okay? That the distribution of k linear forms is going to look like a k-dimensional Gaussian. So both GOWZ and Harsha-Cliven's Mecca proved central limit theorems of this form. GOWZ built heavily off of previous work of Mossel. They gave a CLT where the error bound for a k tuple of half-spaces scaled polynomially in k. Okay, so they kind of lost the fight already here in terms of getting a logarithmic dependence on k. Their CLT's error bound is polynomial in k, not polynomial in log k. Okay? On the other hand, Harsha-Cliven's Mecca took a somewhat different approach. They were able to get a CLT where the error bound scaled only polylogarithmically in k. So these guys are still in the game. They might potentially be able to get some, log k type seed length out. Okay? So the next stage, let's zoom in on Harsha-Cliven's Mecca, see what they did. They managed to fool, again, intersections of regular half-spaces. Like I said, they came up with a central limit theorem for intersections of k half-spaces where the sort of error bound was only polylogarithmic in k. They were also able to de-randomize it, again, with only a polylogarithmic in k seed length. But then the last step, right, ideally we'd be able to extend this to general half-spaces. The last step, where you reduce an intersection or a k tuple of general half-spaces to just regular half-spaces, this doesn't work with a polylogarithmic dependence on k. Okay? Another way to say it is that you can do this if you're willing to assume that k is at most linear. You can get something non-trivial, and that's exactly what GOWZ did. They pursued this sort of multi-regularity lemma, right, where there's a dependence on k. This introduces another polynomial dependence on k. But it doesn't seem as if it's possible to do this regularity lemma-based approach for k being, say, a linear number of half-spaces. It looks like this approach really inherently gives you at least polynomial dependence on k. And it's easy to see why, just with, again, sort of a cartoon picture. Suppose you're trying to work somehow with an n tuple, so k equals n. You're trying to work with n many half-spaces. And maybe your first half-space is non-regular because the first weight, W1, is very large. Your second half-space is non-regular because the second weight is very large. The ith half-space is non-regular because the ith weight is very large. Well, you're in trouble, right? You would like it to be the case. None of these half-spaces are regular. You wish they were all regular so that you could use your theorems for regular half-spaces. But if you want to make them all regular, I don't think there's anything you can do but just restrict all n variables, right? And if you do that, of course, you're doing something trivial. You've kind of lost the game.
So somehow in this approach, we are trying to fold the half-spaces individually. Potentially, you could try to fool the polytope without trying to fool each of the half-space individually.
Potentially, yeah. I mean, I guess if you do a lousy job on one half-space, it seems like it might kind of sink the whole enterprise. Yeah, I like the idea, but I don't know that anyone has sort of succeeded in going down that path. Yeah, so this is just by way of sort of indicating, I guess I'm basically making an excuse here, giving an explanation for why the GOWZ result, the guys who could fool an intersection of arbitrary half spaces, this is one of the reasons why they have a polynomial dependence on K, because just this aspect of getting it to the regular case is going to incur sort of a linear dependence on K here in terms of the number of guys you have to restrict to make it regular. And I'm also kind of explaining why Harsha, Clivens, and Mecca ended up with the result that they did, right? They had their central limit theorem with a great dependence on K. They de-randomized it with a great dependence on K. But it doesn't seem like there's a way to sort of take the last step and have the regularity lemma type part of the argument go through with a polylogarithmic dependence on K. Okay, there seems to be some kind of barrier here. So you have to do something different. And I guess in the remaining time, which looks like a little bit of time, I'll tell you about what we did, or some of what we did, which is coming up with this PRG for intersections of low-weight half spaces. So at least in some, hopefully non-trivial case, we're going beyond sort of this regularity issue and handling a very large number of half spaces, K half spaces, still with a polylogarithmic dependence. Okay, so one of the key, sort of the key starting point for what we do is a very simple fact about low-weight half spaces. So again, we're only going to be dealing with half spaces where each integer weight is at most t. Okay? We call this so-called regular or sparse dichotomy. What does it say? It says if you have any low-weight half space, any weight t half space, then it's got to fall into one of two categories. It either is epsilon regular, right? Maybe it's regular in the first place, like the majority function. It's low weight, nice and regular, you're happy. Or if it's not regular, it can't have very many non-zero weights. It has to be a sparse half space, okay? And this is really a triviality once you formulate the statement, right? Suppose you have a weight t half space, a half space where each coefficient is at most t, integers between minus t and t. Well, if it's sparse, you're happy, it's sparse, okay? And if it's not sparse, what does it mean? It means it has a lot of non-zero coefficients. They're all at least 1. They're all at most t. So how non-regular can you be? Regularity means that the biggest coefficient is small relative to sort of the scale of all the coefficients, a simple calculation. Right? This is obviously the worst possible half space of weight t if you're trying to make it non-regular, and it just can't be that bad. Okay, so this is really a kind of trivial statement, but it's useful for us. And I should mention the fact that we have sort of a linear or quadratic, a polynomial dependence in t here is directly why we have a polynomial dependence in t in our result. Okay? So this regular or sparse dichotomy pretty immediately leads us to the realization that we need to be considering a different pseudo-randomness problem, not really fooling just an intersection of half spaces, but an intersection of half spaces ANDed with a CNF. Okay, the regular or sparse dichotomy, like we said, every low-weight half space is either regular or sparse. So if I think about a general intersection of low-weight half spaces, what should I do? Well, I should sort of put them into two buckets, right? I should take all of the regular guys and put them over here. The AND of all of those guys is going to be this intersection of regular half spaces. I'll call it G. And then all of the sparse guys, all the guys who are not regular or sparse, t over epsilon squared sparse, I should take all of those sparse guys, AND them all together, and put it over here. So what is this really? What is this H? Well, it's the AND of a bunch of sparse half spaces. I just care that it's the AND of a bunch of juntas. It's the AND of a bunch of t over epsilon squared juntas. And I can think of an AND of a bunch of small width juntas as just a small width CNF formula. Okay? So if I want to fool this class of intersections of low-weight half spaces, I just need to be able to fool the Harsha-Clivens-Mecca class, intersections of regular half spaces, ANDed with small width CNFs. Okay? Good. So are we done? That would be nice if we were done, right? We could just maybe combine known pseudo-randomness results against each of these classes. We have Harsha-Clivens-Mecca, who fool intersections of regular half spaces. And for 30 years, people have been fooling small width CNF-DNF formulas with a range of different techniques. Well, unfortunately, we're not done yet. One reason we're not done is that there isn't generic sort of technology for composing PRGs in a nice way. If you have a PRG which fools a class of functions G and a PRG which fools a class of functions H, we don't know of generic techniques for saying, oh, by combining the PRGs, I get a PRG which fools G and H. Okay, it just doesn't work that way. So that's one obstacle. We got to actually do something. A second kind of conceptual obstacle is that the techniques, if you look at them, that sort of go into fooling intersections of regular half spaces, they don't really look all that much like the techniques that fool CNFs generically. Right? There's sort of a lot of analysis going on in these kinds of arguments. It's based on Taylor's theorem, and you pass through Gaussian space, blah, blah, blah. Whereas with the CNF, DNF kinds of things, it's more combinatorial feeling. You use bounded independence or epsilon biased sets or things like this. Okay? So there's some work to do. And I guess if you want to say that there's a conceptual contribution or sort of what are we doing here, one thing that you can potentially get out of looking at what we do is we kind of combine these techniques, right? So the overall strategy we take is really very similar to that of Harsher-Cliven's mecha. It's the exact same generator. We just ramp up the parameters. We need to ramp up the parameters to some extent. But the analysis, in order to prove that it actually works, we have to sort of bring in ingredients from the more combinatorial line of work on fooling, say, narrow CNF formulas. In particular, in the kind of hybrid argument, which is at the heart of these proofs, we have to do sort of a careful coupling in order to make the analysis go through for us, and the coupling is based on pseudorandom generators for CNF formulas. So I'll tell you a little bit about this, more about this in the rest of the talk. Okay, so let me just highlight kind of in a little bit more detail what's going on, and in particular the challenge that having this CNF to deal with presents to us when we want to make a hybrid argument go through. So this is going to be a little impressionistic. The whole rest of the talk will be a little impressionistic, but hopefully it gets across some ideas. Recall in the most basic case of the problem, suppose we have a single epsilon regular linear form, and we're just thinking about like the Berry-SAN type proof, right? This hybrid argument where we replace one variable at a time, x1 through xn. Okay, our single linear form looks like this. And intuitively, at the ith stage of the hybrid argument, what are we doing? We're swapping out xi for gi, for the Boolean thing for a Gaussian thing. Think of it as analogous to just flipping the ith coordinate. It has something to do with like, changing the ith coordinate. So let's just think about flipping the ith coordinate, the ith bit. Well, if I flip the ith bit of a regular linear form, right, what is that going to result in? It can't change the overall sum by very much. It changes it by at most 2 epsilon. Okay, and this kind of thing comes up in the Taylor's theorem type analysis you really do in the formal argument, that each coordinate doesn't have a big influence on the overall outcome. Okay? Similarly, if we have a k-tuple of regular linear forms, like Harsher-Cliven's mecha do, now it's a k-dimensional random variable, but again, flipping a single one of our n input coordinates, right, isn't going to change this vector very much. Each individual coordinate changes by at most a small amount. So it still seems like it's doing a bounded kind of damage. You could imagine maybe doing a Taylor's theorem argument still in this kind of circumstance. In the case where we're dealing with a k-tuple of linear threshold functions and a CNF, though, now the relevant random variable, I think, is really this k plus 1 dimensional random variable. We have, again, a k-tuple of linear forms, okay? These are these regular guys, but we also have this sort of discrete combinatorial thing, the CNF formula, right? That's like the last coordinate that we need to worry about. And this guy's kind of annoying. He takes +1, -1 valued outputs. So in particular, flipping just a single bit can now have a dramatic effect on the overall k plus 1 tuple, right? Flipping a single coordinate can, change the CNF from being satisfied to unsatisfied or vice versa. So this last coordinate can change by a lot. It can change by 2 when you just flip one coordinate. And that doesn't seem very compatible with like a Taylor's theorem type argument or a hybrid argument to show that sort of at each step, the change is small. So the way we get around this is by doing sort of a coupling, introducing a coupling kind of idea into the hybrid argument. So I'll sketch that. Again, we're doing a hybrid argument. It looks at the big scale very much like sort of the hybrid argument we sketched earlier with Mecha-Zuckerman, or also this is what Harsher-Cliven's mecha essentially do. We first pseudo-randomly hash the variables. So intuitively, this is good for the regular part. The regular linear forms, all the variables get kind of spread out across all of them. So we've got these buckets. This is a picture of essentially the ith stage of the hybrid argument. Okay? At the ith stage, we've sort of already filled in with true randomness all the variables in maybe these first i-1 buckets. The ith stage of the hybrid argument, we're going towards pseudo-randomness. So we have pseudo-random, in particular, some kind of R-wise independent distributions filling in all of the later buckets. And to analyze the ith stage of the hybrid, we have to think about 2 different ways of filling in the ith bucket. It's either filled in truly randomly or it's filled in pseudo-randomly. Okay, and we have to argue that somehow the function can't really tell the difference very much between the 2 ways that we fill in this ith bucket. That tells us that this error at one step of the hybrid is small. Okay? So standard hybrid arguments just say that, hey, you don't incur much difference if you fill in that ith bucket in the green way, uniformly, versus pseudo-randomly in the purple way. Okay? What are we going to do? The way we're able to make the analysis work is by thinking about filling in, again, the ith bucket either uniformly or pseudo-randomly. But to make our proof work, we needed to think about having the pseudo-random distribution, that way of filling in the bucket, be kind of carefully coupled with the truly random way of filling in the bucket. And I'll try to explain why this was important for us in the next slide. So again, what are we doing here? We have this sort of coupling of these 2 adjacent hybrid random variables. I'm zooming in now just on the ith bucket. So all the other buckets have been fixed in some sort of way. Let's think about the function restricted to just this ith bucket. Okay, so now I'm thinking about this intersection of half spaces f prime, where again it breaks down into a part which is an intersection of the regular half spaces and a part which is the C and F portion. Okay, all the other variables have been fixed. We're just dealing with the variables in this ith bucket now. Okay, what do we know about what happens to this C and F formula? Well, this nice work on fooling C and F formulas, Bazzi and Razbarov and so on, tells us that the C and F formula here, this small width C and F, is fooled by some kind of R-wise independence. If we fill in the bucket in an R-wise independent way, that's going to do the job. It'll fool the C and F portion of the function. Okay? Having such a theorem, we can think of that as being equivalent to telling us that there's a coupling. Right? Fooling, the fact that R-wise independence fools H prime tells us that it's really equivalent to just saying that there's a coupling between uniform randomness and this R-wise independence, such that under that coupling, so I think of a joint distribution over x and y now, under that coupling, the probability that H prime disagrees on x versus y is extremely small. So I've kind of synced up what happens in the discrete part in the truly random case versus the pseudo-random case. This has the net effect, essentially, of getting rid of this issue of like, oh, the last coordinate is sometimes going to be 2 under a change. We sort of align the changes, and we don't have to worry about them then when you do the analysis. So this coupling is really at the heart of our argument. Just to say another word or two about why it's useful for us. Again, this is just the same picture we saw before. We fill in the earlier buckets uniformly, the later buckets with R-wise independence, and to analyze the ith stage of the hybrid argument, we fill in the ith bucket either uniformly or pseudo-randomly. So it's kind of the ith stage going one way or the other. When we think about coupling these two distributions, the way I explained in the previous slide, according to the outputs of the C and F portion, so that the C and F portions almost always agree, we get a coupling over these two k plus 1 dimensional random variables, this vector valued random variable we saw earlier, where the first k coordinates are what the linear forms spit out, and the last coordinate is what the C and F spits out. And thanks to this coupling, right, if I have the truly random distribution versus the pseudo-random distribution, I kind of have a pair of, I have this guy under true randomness, comma, this guy under true randomness. That joint random variable, that last coordinate is going to almost always agree, right? And that's helpful for us for like a multidimensional Taylor's theorem kind of thing. It sort of takes away, like I said before, this possibility that we have a big difference because of this last coordinate, okay? So this is kind of a key aspect of our analysis. This is not a precise lemma statement. I should have lemma in quotes. But the idea of what sort of the key lemma in our work says is that the ith step of the hybrid argument can be made to go through. If you fill in that ith bucket uniformly versus pseudo-randomly, then the expectation is preserved under these two settings. Actually, what's happening is all in the case of the smoothed function, and you have to do more work later to transform to sort of the sharp threshold kind of thing, but this is the high-level idea, that the ith step of the hybrid can be made to work. And for our proof of this, again, the way we were able to argue it was kind of crucially using this coupling between the true randomness and the pseudo-randomness. So I just have one or two more slides, really a very, very cartoony version of some of the issues that come up when you try to push this high-level idea through. So one challenge is that if you think about having this kind of coupling, it actually breaks some of the nice properties which seem to be important in having the proof of the Berry-SAN theorem go through. When we do this coupling, it actually ends up introducing independence across the different buckets, which is like saying you now no longer have perfect independence across the different things you're summing up. Why is that the case? Well, the coupling for this ith bucket, right? Remember, we sort of designed the coupling for this bucket according to the CNF formula restricted to that ith bucket. What is the CNF formula restricted to that ith bucket? It really depends on how the other variables were filled in. So if you, assign bits to the variables in all the other buckets one way, you're going to get one CNF formula. If you assign it in a different way, you're going to get a different CNF formula. So the coupling depends on the stuff in the other buckets. You no longer have independence between what's going on in the ith bucket and what's going on in the other buckets. So this feels like some kind of a challenge. Turns out you can get around it by doing kind of some approximation. How can I say this? Again, we're dealing with two distributions. The one distribution is where we fill in the ith bucket truly randomly. The other distribution is where we fill in the ith bucket pseudo-randomly. In the case of filling in the ith bucket truly randomly, we're going to look at that distribution as a mixture of two distributions. One distribution corresponding to when the CNF is true, the other to when it's false. In the case where we fill in the ith bucket pseudo-randomly, it turns out that we look at the distribution as corresponding to a mixture of three distributions. One when the CNF is true and it syncs up with the true thing being the true randomness guy being true. Remember, these are coupled. Another when the CNF is false under true randomness and pseudo-randomness, and one tiny piece of the mixture where they disagree. It's tiny, so we don't need to worry about it. Okay? So basically, we're either expressing or approximating each of the two relevant distributions by a mixture of two distributions. Okay? And it turns out that for each of these components in the mixture, you do achieve this kind of independence. You have to be kind of careful in setting the random variables up in the right way to make this go through. We had a number of false starts in trying to do it, but you can kind of decompose the distribution either exactly or approximately in the two cases of true randomness versus pseudo-randomness into a mixture where each component of the mixture you do have this kind of independence between different buckets, which we seem to need to let the proof go through.
This is the same as saying that there is some low entropy random variable like entropy constant, 1, 2, 3, whatever, conditioning on which makes the distribution independent, like product.
Yeah, you can think of it that way. Yeah, that's an equivalent statement of the mixture. Good. Another thing ends up breaking as a result of doing this, thinking of it from this mixture point of view. When you think of it from this mixture point of view, it turns out that while you sort of had perfectly matching moments for the overall distributions, truly uniform versus truly R-wise independent, once you break it up into a mixture of two things constituting uniform and a mixture of two, ignoring the third little error thing, constituting the R-wise independent, now you no longer have perfectly matching moments in these two cases. So that's another thing which we kind of wish we had for the purpose of the proof. But it turns out that by looking carefully at what's going on, the moments don't match perfectly, but you throw a little bit more randomness into the seeds, you hit it a little bit harder, and you can make the moments be very close. You can give up perfectly matching moments and have very close to matching moments, which are good enough to let the proof go through. So this is really getting very impressionistic. I don't want to say more about it than this, but hopefully this gives you some sense of the high-level sort of new insight in terms of making the hybrid argument work was doing this coupling. We didn't see how to sort of relate the expectations without coupling the two distributions, which are the key distributions in the hybrid. That was something that at least we hadn't seen in previous Berry SAN type proofs. And then there are some obstacles which arise as a result of doing that coupling, but you can get around those obstacles. Okay, so this is almost my last slide. Just to remind you again of the result. The result is a pseudorandom generator for these intersections of kind of special low-weight half-spaces. Our dependence, again, is it's what we want in terms of the function of k. It's polylogarithmic in k. It's not what we want in terms of the dependence on t. It's polynomial in t, and polynomial in 1 over epsilon also. So previously, like I said before, we weren't able to really say meaningful things about fooling intersections even of weight 1 half-spaces, but we can say something about that now. And on a technical level, right, the whole thing is based on, again, this sort of connection between CLTs and pseudorandom generators, these hybrid type proofs of CLTs giving us pseudorandom generator constructions and analyses, and we had to sort of think about this aspect of coupling the two distributions in order to make the proof go through. So if you're looking for something to do, I think there are some nice goals for future work here. In particular, like we covered earlier, it would be great to have a result where this dependence was log t. It would be even better to have a result where the dependence is log log t. And saying log log t is just like saying there shouldn't be any dependence on t at all. Right? So the ideal result, you'd be able to completely get rid of the dependence on the weight. In fact, you'd like to even do better and not only get rid of the dependence on the weight altogether, but not have this poly 1 over epsilon dependence. Instead, have a poly log 1 over epsilon dependence. Remember, Mecca-Zuckerman were able to get this. They used branching program-based kind of ingredients on top of what they did for half spaces in order to achieve this. Gopal and O'Donnell, Wu, Zuckerman were able to kind of slam through the branching program aspects of the analysis because they were paying a linear dependence in k. But if you want to be paying a polylogarithmic dependence in k, it's not clear how to preserve this good dependence on epsilon, have it be polylog instead of log. So I think there are definitely directions for future work. And in particular, I kind of feel like this, this might be doable. Anything might be doable, but this might really be doable. Okay, so that's it. Thanks for your attention.